The one-way routes connecting towns A, M, C, X, Y, and Z are shown in the figure below. The distances in kilometers along each route are marked. Traveling along these routes, what is the shortest distance from A to Z in kilometers? So with a bit of trial and error, we can find the shortest path from A to Z, and intuitively we want to use the shorter edges when possible. So we can go from A to M directly with an 8-kilometer route. However, this is not optimal because we can go from A to X and then to M, taking 7 kilometers to get to M instead of 8. Now from M, we can go directly to Z with a 25-kilometer route, but a slightly better way is to go from M to C to Z. This will take 24 kilometers instead of 25. However, this is not optimal. The optimal solution is to go from M to Y to C, and then finally to Z. The total length of this path is 5 plus 2 plus 6 plus 5 plus 10, which is 28 kilometers. Now, because 28 is the smallest out of these 5 answer choices, we can immediately conclude that the answer is A, 28. Now, this may be a bit unsatisfying because without these answer choices, how do we actually prove that 28 is the shortest distance? The way to show this is with a pathfinding algorithm called Dijkstra's algorithm. The idea is that we're going to compute the distances from A to every other point or every other town in this network, starting by labeling the number 0 at A. So what we're going to do is we're going to visit each vertex by order of distance from A. And then for each vertex, we'll look at the edges going outward from that vertex, starting with X, because X is the closest town or vertex to A. And by doing so, we can find the distance from A to every other town or vertex in this network. So starting from A, we're going to first assign a value of infinity to every other town. This infinity just means that it has not been reached yet from A. Now, starting from A, we can go from A to X with a path of length 5. So we're going to update the distance from A to X with the number 5. We can also go from A to M with the path of length 8. As we saw earlier, this is not the optimal solution, but the algorithm, Dijkstra's algorithm, is actually going to update these shortest paths as we visit towns. So once we finished going through the edges going outward from A, we can now mark A as visited. Now we look at town X because X has the shortest distance from A, and we look at the two edges going outward from X, which are the 10 and 2 edges. We see that if we take the shortest path from A to X and then take the edge from X to M, this will improve our distance estimate and give us a shorter value for the distance from A to M. We also visit the edge X to Y. This will mean that the current distance from A to Y is 15. So now we have looked at the edges going outward from town X, so we can mark X as visited. Next, we look at town M because M has the smallest distance estimate out of the vertices or the towns that have not been visited. And we do the same thing. We look at the edges that go outward from M and update the distances accordingly. So we see that if we take the root or the edge from M to Y, this gives us a path of length 13, which is less than 15. If we take the edge from M to C, this gives us a path of length 21. As we'll see, this path is not optimal. And if we take the root from M to Z, this will give us an estimate of 32 for the distance from A to Z. Now, 32 is one of the answer choices, but as we saw previously, 32 is not the shortest path. This is because we have not visited every vertex yet. Okay, next, starting with Y, we look at the edges going outward from Y and update the distances accordingly. So the distance from Y to C is 5. So if we take the root from Y to C, this gives us a path from A to C of length 18. If we take the path from Y to Z, then this gives us a path from A to Z of length 30. 30 is less than 32, so we update the estimate. So we have now visited vertex Y. Lastly, we look at vertex C and look at the edges going out from C. And we see that only the edge from town C to town Z is the only outgoing route. This will improve the distance from A to Z from 30 to 28. And lastly, Z has no outgoing edges, so this is the shortest path from A to Z, which goes through every town in this network. So by running this algorithm, Dijkstra's algorithm, on this particular graph, this rigorously shows that the minimum distance from A to Z is 28 kilometers.